Lesson 4.3, Graphs of Polynomial Functions. Just a recap of what we discussed in class. Today's mastery objective is to identify the properties of general polynomial functions, which include continuity, end behavior, intercepts, local extrema, and points of inflection. We have a lot to get to, so let's get going. First of all, we are going to go beyond first-degree polynomial functions. First-degree polynomial functions are lines. Graphs of second degree or quadratics are called, as we know, parabolas. What we're going to do is look at higher degree polynomial functions that have a degree greater than 2. So the basis of those, kind of like a parent function, would be this, where a is a constant and n is a non-negative integer. So we're looking at functions as the parent function where we have things like f of x equals 5x to the third. Well, we break those up into two types. If they're of odd degree, where n is odd in this model, we'd have graphs that look like this. Notice they're both kind of like these zigzag type graphs, either in quadrants. In this one, quadrant 1 and 3. In this one, quadrant 2 and 4. How we get those two different graphs is based on, you can probably expect A. If A is positive, we'd see the graph, something like the graph on the left. If A is negative, we'd see the graph on the right. If the polynomial function is of even degree, if n is an even whole number, then we'd see graphs that look like this, either opening upward or opening downward. This parabolic type shape, symmetric with respect to the y-axis, and a greater than 0 gives the graph on the left, a is less than 0 would give the graph on the right. So there is a number of properties we can look at one at a time and see how they play themselves out in the graphs of these polynomial functions. The first is continuity. What we mean by continuity is that polynomial functions are unbroken curves with no jumps, gaps, or holes. If you had to draw a polynomial function, you could do it without lifting your pencil because there's no breaks in the graph, no holes, no gaps. And here are two examples from your text, which are examples of non-polynomial functions. What we mean by jumps is the graph would go along. We've seen this with our step function, greatest integer function, where there's a jump. That would not be a property of a polynomial function. Some functions actually have holes in them at particular points, where there's no value here, and then we're trying to show the absence of that. This is an example of a sharp corner or a cusp. We don't have those with polynomial functions. And over here we see another example of a cusp or a sharp corner, and then when there's a gap, that would probably be from a vertical asymptote. So none of those things happen with polynomial functions. End behavior is the shape of the graph at the far left and far right of the coordinate planes. We talk about the end behavior of a function. We talk about looking at it when values of x, the absolute value of x is large. That would bring us, if the absolute value of x is large and x is negative, that would bring us way to the left of on the coordinate plane. If x is a positive number and the absolute value of it is large, it would bring us way to the right. When the absolute value of x is large, the graph of a polynomial function closely resembles the graph of its highest degree term. What we mean by that is if you look at this polynomial function defined as 2x to the fourth minus 5x squared plus 2, it looks kind of like a W. But what we're really looking at is how does it behave way over here and way over here. And you can see that the graph, as you go farther and farther to the left, it's getting larger and larger clearly. When you go further and further to the right, it's getting larger and larger, growing. It's increasing without bound, we say. So it never stops growing. Well, if you take the first term and consider a function of that form, you can see that this function does the same thing as you go to the left. It gets larger and larger. As you go to the right, it gets larger and larger. So if you were curious about how a function like this behaved as you went way left and way right, all you need to kind of focus in on is this term. These obviously play a part in changing the shape of the graph from this more basic graph function to this. But as far as the end behavior, it's all dictated by that first term. Similarly, here is a function that is defined as negative 3x to the 6 plus 5x squared plus 2. As you go way to the left, it's decreasing without bound. As you go way to the right, it's decreasing without bound. Approaching negative infinity, we say sometimes. Well, so is this. This represents the first term over here. And this could have been one of our first functions we looked at here just a few slides ago. It's decreasing without bounds. You go way to the left, and so is it when it goes way to the right. So if you want to know how this function f was behaving, just look at the first term. Consider this. It does the same thing. Same with functions of whose largest degree term is odd. This function kind of starts low, ends high. So does this function, which represents a function with only its first term. This function starts high. As I say, starts high means when x is very small, it's positive values. Ends low, ends with negative values as you go to the right. And this is dictated or given or revealed by this first term. Next property are intercepts. A polynomial function of degree n has one y-intercept and at most n x-intercepts. The y-intercept is really the constant term, because if we let x be 0 in all these terms, remember y-intercepts are found when x is 0, so f of 0 would be, in this example, 10, and that's the constant term. And the x-intercepts are really the zeros of this. So this being of degree 7, we know that at most we're going to have 7 zeros, so there'll be at most 7, or n representing the degree of the polynomial, that number of x-intercepts. In this example, which we actually did as a warm-up in class, we looked at as a warm-up class, its degree is 7, the y-intercept is 10, and the x-intercepts are these 1, 2, 3, 4, 5 numbers, where negative 5/3 and 2 are the rational zeros or rational roots. These other 3 were found with our calculator, but we sense they are irrational. Next property of polynomial functions is multiplicity. Multiplicity has a way of having us figure out how graphs relate to the rule. If x minus r is a factor, then we know that r is a root. But if it occurs m times, then r is called, then we say that r is a zero of multiplicity m. So in this example, we would look at this in factored form and realize that negative 1, positive 1, and 3 are all zeros. The multiplicity of them are different though. Negative 1 is a zero of multiplicity 3 because it's raised to the third power. 1 is a zero of multiplicity 1, and 3 would be a zero of multiplicity 2. If we look at this graph, and this is a graph we saw in class at the beginning of class, but if we look at this graph, we can see the existence of the negative 1, the 0, negative 1, the 0, 1, and the 0, 3. And you'll notice in this case, when the 0 was negative 1, the graph intersected the x-axis there. And same thing happened here at 1. But at 3, the graph has a value of 0 at 3. But in this case, a little different. It doesn't cross through the axis. It actually is tangent to it. It touches once but does not cross. Also, before we leave this, notice the y-intercept negative 10, which we expected. Also, if we did expand this, it would be of degree 6, and we would expect it to behave like a polynomial function of degree 6, ax to the 6th for its end behavior, and starts high, ends high. Well, as far as multiplicity is concerned, if C is a zero of multiplicity K, if K is odd, like it is here and here, this one's cut off, but if it is odd, the graph will cross the x-axis at C, like it does here at -1 and 1. If it's even, the graph will touch but not cross, as that's what happens at 3. Remember, this is, if you can't see it because I've covered it up, but this is x minus 3 to the power of 2 to the second power, multiplicity 2. So again, just to go back to some real fundamental functions and see how this plays itself out, notice again, even, 0 is a 0, or root, and the graph just touches at 0 because it's of even multiplicity, doesn't cross. Whereby here, this is odd multiplicity, and so at 0 being a 0, or root, the graph doesn't touch and go back down, it crosses. And we move on to local extrema, which is actually the plural of extremum. A local extremum would be a max or min. These are points that are local maxes, local maximums or peaks, or local minimums, which are valleys. A polynomial function of degree n will have at most n minus 1 extrema. That means that there'll always be at most one less than the degree of the polynomial number of peaks or valleys. At most, that many. Points of inflection. This is again where the concavity of a graph changes. This was introduced to us. It's a fairly new idea. The graph of a polynomial function of degree n with n greater than or equal to 2 has at most n minus 2 points of inflection. So if the degree is greater than 2, which we're going to be looking at most of those, there'll always be 2 less than the degree points of inflection. And if it's an odd degree polynomial, it'll have at least 1 point of inflection. So we look at this example that we looked at earlier. The number of points of inflection, we'd say that this would be a point of inflection going from concave up to concave down. Another one right here, where it's going from concave down to concave up. So that's our second one. Concave up to about maybe somewhere in here. That's our third one. Then it's concave down till about here, which would be our fourth one. And then it's concave up the rest of the way. So for this polynomial function, remember it was degree 6, we get 4 points of inflection. Again, right here is our second. This would be our third. And this would be our fourth. So that's an introduction to those. The rest of the lesson, we'll look at how all these things together complete a graph of a polynomial function and how we can analyze graphs of polynomial functions by tying all these ideas together.